Hi everyone, good afternoon. It's great to be back, so thank you very much for having me. As Sam said, I've been here a couple of times before, giving talks on how to model circulating fluidized beds for sugar cracking into biochemicals, which is what I would consider sort of normal applications for Barracuda. Today I'll be talking about CFD analysis or CPFD analysis of sand and gravel filling in seabed socket for wind turbine tower, which is, at least according to my point of view, a bit outside the scope of what we normally do with Barracuda. But I work at a consultancy called Aerotak, and we don't do a lot of fluidized bed simulation. So even though I have a background in that, it's not something we do a lot in. We do a lot in process industry in general. I'll come back to that in a bit. But the whole point is for us to be able to deliver some value proposition to customers, we need to make sure that we're using the right tool for the right tasks. And I think in that context, Barracuda can be used for a lot of other things than just fluidized beds. And I think that's what I at least hope to show you today. But perhaps a bit more background into Aerotak. So we are a Danish fluid mechanics consultancy, at least that's what we call ourselves. We were founded back in 2017. We started out as 2 people, and then I joined in the late autumn of 17, so 3rd person. Now we are about 20 people. We have an office in Copenhagen, where I'm based, and then we have an office in the UK near Oxford that does aerodynamics on cars. Most of what I work with is within process engineering, working for companies like Novo Nordisk, Carlsberg, FS Mid as well, doing cyclones, doing spray dryers, stuff like that. But we also have a lot of other things that we're working with. Generally, I think 90% of what we do is CFD related. We have a different set of software, a different set of tools that we use depending on which type of customer we're working with, which type of process, which type of unit operation. So we're able to select the proper tool for the specific task. We also do other things such as 1D tools, 2D tools, which is coming up. So we can basically make a tool, heat and mass balances, deliver that to the customer, and they can basically play around with it themselves without having to contact us to do a full simulation that maybe takes a couple of weeks to perform, set up, post-process, and report. So really giving some power to the customer themselves. And then we also do other types of consultancy jobs in terms of just advising on how to operate different units. We do on-site measurements, controls, stuff like that. I'm going to skip this, it doesn't really matter. I think these are some of the unit operations that we normally work with. Spray dryers, cyclones, wet and dry, mixing vessels also with chemical reactions in there. So this is sort of what we normally look at, and I would basically be able to take any one of these cases, take them out, present, and then show how we do it at Aerotak. But I think in this case it's a lot more interesting to actually take a case where we've actually used Barracuda. So we are using Barracuda in a few cases at Aerotak. It's not a lot, but we're trying really to get the ball rolling. Doing some fluidized beds, you do see one here in the top left corner. But we need to be a bit creative in terms of where we actually use Barracuda. That's where I started my presentation. And this is a case where I think we have been, I wouldn't say too creative, but at least to some extent creative enough. So basically, we had a customer coming to us. Actually, it was a referral from one of our competitors who said, we've gotten this request for a simulation, we can't do it. We don't have the either skills or tools to be able to do it. Can you help them? So we said, let's at least talk to the customer and see what's about. So basically, the customer is a Danish company that is specialized in transporting sand from one place to another, basically. And that can be used in a lot of different means or in a lot of different processes. But what they're using it for in this specific case is to fill up, or basically fill up socket holes in the seabed with sand and gravel, because you need to prepare the foundation if you're putting a monopile structure on it. So for example, let's take a wind turbine tower, if you have a gravity-based structure that needs to be just placed on the seabed, or this type of tripod structure, then you need to make sure that you have a proper foundation so that there's nothing moving around them there. So basically, they drill holes, pull in the sand, fill it up, stack it, and then they do that a number of times, and they have a proper foundation. But there are a number of things that can go wrong in that filling process. There are a number of different variables and evaluation parameters that need to make sure is sort of that they live up to. And there are different ways of filling these holes. Some of them are quite complex, perhaps very efficient, but basically in the end, we just need to fill up a hole as easy as possible with the best possible outcome. It's very difficult to go out to the seabed 30 meters below the sea level to do measurements and investigations on have we actually done a good job or not. So how can we actually do something in advance of this filling to evaluate whether one solution is better than the other? So basically the objective here was to make a CFD model that allows us to evaluate the following parameters. One, because we're working with sand and gravel, that of course has a particle size distribution. And we need to make sure that within the height and the radial distribution of the socket, this hole, that we actually have a nice distribution of the particles. We don't want very large particles on one side and small particles on another side, evenly distributed. Secondly, we want to make sure that as we're filling up the socket, and in the end, upon the end of the filling, that we don't end up with very large variation in the surface contour of the filling. So ideally, we would like it to be just flat. If there are large holes or bores or whatever, then that's an issue. So we need to be able to evaluate that as well. And the last thing, which is it's not the most important thing, but is quite important, of course, is that if we're filling up this socket, naturally you have current and everything like that going on top of the seabed, and we don't want to lose all the sand that we're pumping in. So we want to make sure that the sand that we put in stays in the socket. That's better for everyone. So the question then becomes, I'll take that in a bit. I have another slide first. But just to set the stage for what it is that we're actually looking at, that will be quite decisive for which tool we end up using. So this is a schematic of how the socket actually looks. So what our customer is doing is basically sailing a ship with a large pipe over on top of the socket and then just pumping sand and water through that pipe. And the normal way of doing that is simply to have a long pipe that goes all the way to the bottom of the socket. Then you start filling in the sand, and then you slowly retract the piping as you fill up the hole. That's the best way to do it, basically. It's also quite complex. Mechanically, it's expensive because you need some sort of mechanism that withdraws that, and the whole mechanical structure of the pipe also becomes quite tricky to handle. The socket that we're looking at is divided into two parts. There's a lower socket, which is this 8.5 meters in diameter. It's about 25 meters tall, and then that you fill up with sand. And then on top of that, you have an upper socket that's about same diameter, and then about 10 meters tall. You fill that up with gravel. So it's basically a filling that happens in two stages. Sand first, then gravel. But this is a quite large hole, basically. So it's 35 meters tall, 8-9 meters wide, or in diameter. That gives us a quite large volume that we need to fill up with particles that are somewhere between 0.5 millimeter and 4 millimeters or 5 millimeters in diameter. So the question then becomes, how do we do that? So naturally you have these quite large physical scales. You have large difference between the size of the particles and the size of the hole. We've seen some generators and stuff like that are quite large as well. The main difference here is that we need to be able to actually fill it up completely. So basically at a closed pack volume fraction. The second thing is that filling of this hole, it doesn't take a minute, it doesn't take 2 minutes, it takes hours. So we also need to be able to simulate that entire process. So we have quite large temporal scales as well. To make matters worse, we also need the particle size distribution. And that, of course, is a big issue when we're talking about different ways of simulating granular fluid systems. And we have an issue that in some places of the system, we're going to have low particle concentration, and in other parts of the system, we're going to have completely closed pack. That also makes things a bit more difficult. So when we get a project like that, basically we have a number of different tools that we can use in Aerotak. For the spray dryers, the dilute cyclone, stuff like that, we always tend to use a DPM method. We don't care about particle collisions there. The problem is here we actually need to have some sort of idea about what goes on when particles are hitting each other. So that one's definitely out. Then you have the DEM. We had the nice presentation by Altair. I think in my opinion, we use a different software for the DEM. And even with that, even with the coarse graining approach, I mean, we have to fill in so many particles that it's okay, that one's out. Then you have the two fluid models, the Eulerian approaches. Again, we need a particle size distribution. We could do that with a multi-fluid model, but then I would be afraid that the computational cost just basically explodes. So those are out as well. And that leaves us with two options within Aerotak. We can use a DDPM model. Not really convinced that is a good choice in general. And then we can use the MPPIC. I also happen to have some experience in that. So of course, we ended up going with the Barracuda on that. But and that gives us the possibility to simulate a large amount of particles in this large system. We can do the particle size distribution, check, and we can actually also do high and low particle concentration at a reasonable accuracy. But we still have this large temporal scale, large simulation time that we need to deal with. So in order to deal with that, we were pretty sure that we couldn't handle that on our own very poor GPUs. So we got in contact with Rescale to basically see if we could make a collaboration there to use their platform to run the simulations in order to also tick off the large temporal scale challenge. Okay, but that being said, that doesn't solve all of our problems. So Barracuda is very good at sort of the traditional applications. We've seen that many times today. The problem arises when you have things that start to move in terms of geometry. And here we have a case where we want to simulate a pipe that is retracting as function of time. So how do we do that? The first step, call Sam. Second step, make him do a solution. And third step, implement that solution. Yes, I wouldn't be that good of a consultant if I didn't have Sam on my contact list. Anyway, what we ended up doing was basically saying, okay, let's just forget about the geometry of the pipe. It doesn't really matter. That's not where we're interested in. So we use boundary condition injectors, or these BC injectors, put in a number of these at basically the entire extent of the pipe, put them in a plane that has a diameter or an extent that basically represents what is the diameter of the pipe, and then we can basically turn them off as function of time, and that sort of mimics the behavior that we're interested in. And that also makes it quite agile, because if we want to do something else, for example, just have it steady, then we can turn all the other ones off, and it's the same setup. We don't have to change everything, and it also saves us some cells. The geometry that we're simulating is, on the other hand, very, very simple. I mean, it's just more or less a straight cylinder. We have a bit of the environment on top of the seabed width into the simulation that we can also extend. But generally, that makes it a quite simple simulation setup once we have figured out a way to handle this retracting pipe. I have to say already in advance that this actually turned out a lot better in terms of actually running the simulations than we expected. So we were actually able to do a number of simulations. Originally, we just planned a few because we were like, we don't actually know what is going to come out of this. But it actually turned out great. So we were able to both do simulations with sand, with different operating conditions, with emergency stops, everything like that, because this system, this setup was quite agile, and we can also do the same with the gravel fillings. That was quite a success. I don't have time to go through all of them, but I will go through the comparison between what we call this sand retraction filling, where you basically have the pipe that is retracting, and a top filling approach, where you basically just have the outlet of the pipe placed at the top of the upper socket. What the customer was basically hoping to was to be able to just do this top filling, because it's a lot easier, it's a lot more simple. You just have the particles falling down, or maybe being entrained with the flow of the water. But it's just a lot more simple. So if we can get the same results for those two, then we're basically happy and we can go ahead with that solution. Yeah, so now we did have a bit of an introduction into Rescale, maybe just from a customer point of view, because in that case I'm actually a customer. It was actually, I haven't really used Rescale before. I was introduced to it a bit. This is not a commercial for Rescale. I just wanted to say that the actual workflow of Rescale is quite easy. So you basically just upload whatever you have. You set up, you define what type of GPU do I want to use, how long do I want to use it for, any type of post-processing you can put in directly there, and then you get the results at the end. And for this case that we were running, depending on the operating conditions, a simulation on a V100 card took about 6 to 18 hours, and yeah, it's at a very sort of low cost compared to the budget of the project, but it's also quite agile for us because we don't have the money to go out in advance buy GPUs. So for us, it's a very good sort of a business case that we can just use something that flexible and basically charge it to our customers. Okay, so here's two simulations. This is a bit tricky because they are not in sync. Sorry about that. But basically they compare on the left-hand side the retraction filling to the top filling. So these are particles that are colored by the particle volume fraction. Basically what you can see is that you're filling up the hole with the particles. We're using about 8 million particles. I think it's like 300,000 cells, something like that. So it's not that heavy, but we wanted to run a lot of these simulations, so I think that is acceptable. The biggest difference that you actually see between the two when you actually start to have particles that are settling is that for the retraction filling case, you're able to keep all of the particles in the socket. So you do have a small portion of particles that are sort of swirling around up until the point where you have the pipe located. But in the top filling case, you basically fill up the whole upper and lower socket with particles swirling around, and some of them tend to move outside of the socket, and that's what we don't actually want. Here is, again, two animations, one for the retraction filling on the left and one for the top filling on the right, where we've put a center plane down through the middle. Because one of the other things that we're interested in showing is how does the surface contour of the settled sand, which is marked in red, how does that actually evaluate both as function of space but also as function of time? And what we can see is that for the retraction filling case, there is a quite short distance between the outlet of the pipe and where we have the settled particles, and that basically creates sort of a bore and then a piling of these particles next to, which looks quite realistic, and you get the same type of behavior for the top filling, but only sort of at the end where you have a shorter distance. One of the things that perhaps is, let's say, less physical, or it might be, but we don't actually know. So the amount of data that we have to validate this is non-existent. That is, of course, a drawback when doing this, but I think as long as you are aware of that and communicate that to the customer, that this is a model only, without any direct basis to reality, then I think it's okay. But one of the things that we see is that once the filling stops, we completely level out the contour of the settled particles. We did expect that to happen to some extent, but not to the extent that we see it here, perhaps. So maybe there's something that is a bit off there in terms of the modeling. Yeah. But they behave more or less the same in that manner for the two cases. The last thing that we're interested in looking at is the particle size distributions at different locations in the socket. So what we're able to do at the end of the filling was to basically go in, take out different volumes from different locations in the socket, and then compare how does the particle size distribution look to the original distribution that is marked in a black dashed line. For the different locations. And then we can go in and see, okay, what happens in the center, what happens near the wall, and basically evaluate on that. And that was actually a quite useful tool, also because we could then compare directly for different cases. And that's really where this, the CFD tool in general, and also this here becomes very valuable for us as well as the customer, is to evaluate different cases and compare them to each other. Where one of the cases we're interested in looking at here is, of course, how well does the top filling approach actually do compared to retraction filling approach. And in terms of particle size distribution, not a big effect there. I would have been concerned if all of the plots that we're showing for all of the different cases looked more or less the same, but we actually did see quite a large variation in particle size distributions. There was actually sedimentation that could be proved or seen for different operating conditions. So that basically tells me that for these two conditions, they do more or less well, equally well. The only difference being that for the top filling, we do still see this effect of some particles escaping through the upper socket. So we wanted to investigate that last part a bit more into detail. So we actually added a more realistic boundary conditions on top of the socket, where we have a current of 0.5 meter per second, just to see what actually happens and how does that influence the amount of particles that we lose. So this is again the same type of animation, and then seen from the top with the current coming in from the top, and here you have the current coming from the left. And basically what you can see is that we are still losing particles to the surroundings, and they are forming in a pattern that we would expect based on the separation points of the flow around. Yeah, there's a casing that basically sticks up a meter from the seabed, and then you have some particles being carried downstream with the current. But the amount of particles that we're losing, we could then evaluate using Barracuda and TechPlot, which amounts to about 2 tons, which is a lot. Sounds like a lot, but it's actually a fairly small percentage compared to the amount of sand that we're actually putting into the system. So this was actually acceptable for our customers. Yeah, so with that, I would just like to conclude a bit. I think this was definitely a challenge in terms of figuring out can we push Barracuda, not because it's a tricky case in terms of simulating, but mostly because it has nothing to do with fluidization at all. And I think this was actually a case where we were able to show that we could actually simulate this, we could get results that we could report, that we could basically use to help our customer. And I think that itself is basically a success. And the setup that we managed to do and got help from the support team at CPFD Software to set up allows us to run a number of different studies, sensitivity studies, varying different operating conditions, filling methods. We even put external current on to see how that affected the particle loss. So in terms of that, the key customer takeaway was at least that we can actually do the top filling. It doesn't make a worse filling conditions, and it's a lot cheaper for them to do. So they actually ended up going with that top filling approach. From, let's say, an internal view or a project management view, I think definitely running together with the Rescale setup was quite cheap actually, and allowed us to run a lot more simulations than we expected. And that basically improves the business case for us. The more simulations we can do, the more money we earn. But it also provides a better sort of proposition to our customer, provides more value. They can get better insights into what actually goes on. And then I think this setup of using Rescale is actually quite clever, and I think it's something that we'll do more of in the future, because we don't have to go out and buy a GPU, which we only use for, let's say, a handful of simulations every year. So it's very agile in that sense. And then lastly, I think I would just like, again, thank the support team from CPFD and also the support team from Rescale for helping out on this. That really saves me a lot of hours. So that's appreciated both from my side and from Aerotak's side. Thank you, Frederik. Thank you.
Thank our speaker. Yeah.